In the next two lectures, we're going to look at scene graphs, which are another way to exploit hierarchy and give us really a wholly different view of computer graphics. And we'll start in this lecture looking at sort of the background and what is a scene graph, and basically it's going to turn out to be a tree. And in the next lecture, we'll look at some real scene graphs and even look at an example of a very popular one. So we want to introduce the notion of graphical objects. And so if we look at it this way, you can say, well, we've been dealing primarily with geometric objects. They have locations in space. Anything that's geometry, they have size, they have location. But if you look at other things we've been dealing with, other entities that go into graphics, a light has a position in space, a direction it might be pointing in, so it has some geometry attached to it. So why shouldn't I be able to have a light object just as I might create an object for some geometrical entity, a cube, a sphere, whatever. Likewise, the camera has orientation, it has a location, it has other parameters which we might attach to it, like the near, the clipping volume, but it has, again, some geometry, and we can look at it as a geometric object. But even other attributes have the ability to be looked at as objects, even though they may not have any geometry associated with them. Things like materials, I can think of having a material object that has all of the properties of a particular material, and then I could assign it to different objects. So then here's where the hierarchy and the linkage and the relationships come in. So really, scene graphs are a way first of expressing all of those relationships by all the entities that make a scene. And perhaps that's where the way to start thinking of it is that what I'm trying to do is form an image. An image is an image of a scene, and everything that goes into forming that scene, the objects, the standard geometric objects, the material properties, the lights, the cameras, all of those things are elements that go into that scene. And so the scene consists of these elements which we'll define as objects. Okay, now historically, the path that we got to scene graphs is started with really the limits of immediate mode graphics. So even though we have been doing retained mode graphics, it's worth going back for just a minute to say, remember that the original OpenGL systems and others were based on immediate mode. As soon as you specified a vertex, it immediately went through the pipeline and was joined with other vertices coming down to display objects, but there was no memory associated with it. Once you displayed something on the display, that there was no way to regenerate or move the object. You could regenerate it, but there was no way to move the object or alter it or really do anything with it without redrawing it from the code that specified it. So you always had to go through, just even to simply keep things refreshed, you would be going through the code over and over again. Now, one solution to that was something that came up very early in graphics, which was the display processor. The display processor was something that allowed us to offload this repetitive redisplay on originally very slow, expensive computers to a special device that had memory that stored display files, or what became known as display lists, which described what you wanted to display, and that provided, at least in OpenGL and other systems, provided a partial solution to the problem. The reason it was partial was because display lists, as in the pre 3.1 OpenGL, lived on the CPU side. So in order to re-execute a display list or change a display list, it was difficult because it was basically a static entity. If I wanted to change its contents, I basically had to generate a new display list, destroy the old one, swap the names, and go through the path from the CPU to the GPU, which wasn't really very, very efficient. Well, retained mode graphics, of which in some ways display lists are an example, are that you store the information so that you can change it or or redisplay it. And that's basically what GPUs really support. It was a nice idea, but once we started getting GPUs that had their own memory that they could access so that you could do changes to data that were stored on the GPU and redisplay it very, very quickly, transform it, change colors, move things around. That became really the standard mode to do things. So even if now, as you've seen with all the code we've been working on, even if you're not changing anything, we automatically put all our data on the GPU as just a better way to do things. And so what happened over time was that immediate mode functions just became not very useful for real-time, high-performance graphics, and OpenGL deprecated them, as we know, starting with 3.1. But even with the newer OpenGLs, and even with WebGL, which is just one version of it, it's a relatively low-level API. It still retained the notion that it was close to the hardware so we could get a really good performance out of it. And there were one of the things that we really lacked was any kind of an object orientation. And that was problematic, not necessarily for people who wanted to do their own real-time graphics, but the big community that was using graphics but were not writing their own graphics. They simply wanted to use graphics for CAD-like applications, animation kinds of applications. Writing code in OpenGL to do the kind of high-level things they wanted to do was very inefficient, and it had other problems that would be locked to a particular architecture. The other problem was without having an object orientation, you had certain strange things because OpenGL was very state-based, and so if you took something like in this slide, a green sphere, you say, why is that sphere green? Well, that may sound like an odd notion if you're thinking about physical objects, but if you think about the way that we've been developing a lot of our graphics, greenness is not necessarily a property of the object. It isn't linked to the object. And it was even worse in the pre-3.1 OpenGLs because the current color was part of the state, and everything would be green unless you changed the state. So it wasn't directly coupled to any object, and that was conceptually and practically a real issue. With vertex attributes, you can, as we've been doing them, you could link it, but you don't necessarily have to. If you have, for example, one color for an entire cube, you may want to send that over as a uniform so it's not quite linked to the vertices the way you might want it to be. So we really want to look at things that come from object-oriented programming, both in terms of the language and the kind of techniques that are available to you. So let's take a very simple example. You have in an imperative programming model, sort of what we would do with very basic OpenGL, especially immediate mode. You'd have an application, and the application would generate data. But if you wanted to rotate, say you're generating a cube, as in this example, and you want to rotate it, in order to rotate it, you'd have to know exactly how that cube is represented. So remember when we talked about representing meshes, and we talked about there were varying ways of doing it. You could use a vertex list was one example, an edge list was another example. And if you're thinking about applications which deal with large amounts of data that may come from some sort of CAD application, one of them may use a vertex list, another may use an edge list, another may use some other structure. But in order then to do the rotation, we would have to know exactly how that cube is represented, and the code we would have would be very, very different if the cube was represented with a vertex list than whether it was represented as an edge list. And that sort of violates everything that you've all studied about object-oriented programming. In object-oriented programming, we'd have a very different way of doing things. We would have a cube object, and we would send messages. I mean, that's the standard, I guess, wording, or we would send a message to that object telling it what we wanted to do. So we would send a a message to the cube saying, I want you to rotate yourself. So the idea now is the cube, the object, has the code with it that knows how to rotate itself with whatever representation is it uses, and the application needs to know nothing about the representation. It's just saying do this operation and send a message over to do that. And that's really for these kind of applications is certainly a much better view of things. Although to represent the other side for a second, if you want to do really fast things, then often you need to know exactly how things are represented and write code that's at a much lower level. So there's a place for the real-time sort of OpenGL programming, which we've emphasized in this class, versus the higher level stuff where you're saying, oh, I'm just going to want to put it into the graphics system, and I'm working at the CAD level with some big database. Okay. Now, if you look at how you support this, one way, if you're a C programmer, is you use structs to build objects. A better way is what you do with C++ or Java, where you have classes and you can have both public and private members. If it's C++, you have protected members. But you have ways that you can hide. The principal point here is that you want to be able to hide the implementation of how the data are actually represented from the user. And this is really the whole notion behind abstract data types. So it's a much more general view. Now, JavaScript really has multiple ways of doing object orientation. So in a sense, it's not object oriented, but in another sense, the language is so big that you can do things just like you would do it in C++ or Java. So we can do that. We'll look at it just a little bit here, and then the next lecture we'll look at a particular implementation. Okay, so the idea would be this, that if you defined a cube object, which you could do in JavaScript, using one way is you can do it very much like Java. You can also do it through the JavaScript inheritance mechanism, where every object is a descendant of some master object, even when you may not see that. So you inherit automatically all these methods from its prototype. Now you can create prototypes for a cube, and then which would say be a cube that automatically had white as its color and was centered at the origin with its sides parallel to the axes. Very simple. That would be your prototype cube. And now, when you did new cube, it would create that object, and now it would have members in it that I could now set. I could set its color as some. If in the prototype the color is a 3-element array, I could then set the red, green, and blue values by just saying myCube.color and so on. So this would set it to red. You can attach an instance matrix to it, set the values of the matrix, or just have a function set them. So it's pretty obvious that this is a standard way of creating an object, and the point here is it's easy to do within JavaScript. Okay, and then you could now say, well, I can also have functions that operate on the cube, and this is the sense that the cube knows how to rotate itself and to translate itself. So now you can have operations that take your cube object translated by this example is 1 unit to the right. You can rotate it, in this case, by some angle around the y-axis. You can change its color. So all of those things are standard coding forms that you should all be familiar with. Now, the one thing you may not be as familiar with is that these objects, the terminologies, they know how to render themselves. So the rendering, how you display an object, does depend on how it's represented, but that's something that's internal to the prototype of that object. And so the render method that you now create with that object knows how to take its internal representation and render it for you. So a rendering pass through everything would apply the render method for each object to it. So we say that the cube knows how to render itself. Okay, so now we could look at code. The code might look in an application might look something like this. It would be you have a cube, and so there's lots of ways of doing it. I probably should have left this slide out. Much more, I think the way you would do it is to use sort of the Java, C++ way of creating objects and with the JavaScript prototypes. Okay, now implementation is, you can, it turns out, in JavaScript do the kind of things I'm more familiar with C++, is that C++ has a public part and a private part. It turns out you can do that in JavaScript. It's probably a little bit trickier, but it's all doable. So you can look in the standard references, JavaScript references, to look at examples of doing that. Okay, now what about other objects? That's the more interesting part for us. Is as we said at the beginning, other objects can have geometric properties, like the location of a camera, its orientation, the location of a light source, and if it's directional, what direction is it pointing to. But then we could say, well, if I'm going to make objects out of them, why don't I make objects out of things that aren't geometric? So I can have a material object, a color object, a transformation matrix could be an object, and then I would like to be able to manipulate those things as I manipulate anything else. So you would have code in JavaScript that might look something like this. You would have, well, actually that should say var my cube, new cube, and then you could have a camera. This is more I didn't change this for my C++. You could have material properties and camera properties, and so this is, if I change those to vars, I think you get the idea of what we can do. Now, as I said, in JavaScript we have prototypes. We can create objects with constructors just as we would in Java or C++. We can have methods. We have ways of hiding things so that we have essentially private parts of the object. So the code to use it would say something like my cube is a new cube, and then we could set its color explicitly. We could set its instance transform explicitly like this. So the prototype would give us default values from then, and then we could set them to be whatever we want. And this is just one way to do it, but I think the code is fairly clear. If we wanted to do light, then I would have a prototype of a light object that set the properties of the light to some default value, gray, diffuse, whatever, and then I could then just say create a light by new light, and then start setting its positions, its values of the properties to be whatever I want. So the type field might specify whether it's a directional light or not. Then the position would just be some XYZ or XYZW. If it was a directional light, then I'd want to set the direction it was pointing into. Then the specular, diffuse, and ambient properties would give me the color of that light. And you might want to have other properties in there, different kinds of lights. You may want to have a distant light versus a near light. All of that, once you set up your prototype, easy to add more properties, and you can even do that dynamically. Okay, so now if we go and start looking at the description of a scene, understanding that we can create all of these different objects, we saw, let's go thinking of the figure model, we said, well, I can describe that by a tree, and what I was able to do was write a generic traversal algorithm that would work with any tree that I did that. So the argument now for a scene graph, we're finally at the scene graph stage, is I can say that all the elements of a scene, the geometry of the objects, the cameras, the lights, material, are all objects, and I should be able to put them into a tree where the tree describes the scene. So the idea is that the root of that tree is the scene. Okay, it's at the root node, and in that scene it has multiple objects, each of which can have other objects associated with it. And then I hierarchically, and then I can render the scene. And what does that mean? It means you traverse the scene, and for the geometric objects, you draw those geometric objects out. If it's a material property, it will allow you to change the material. If it's a light source, you can change light sources and have different light sources working on different parts of the scene. Okay, so you get a graph that, again, is a tree. It might look something like this. So you have a scene at the root. You have, in this very, very simple example, you have two objects, a light and a camera. Each of those objects has sub-trees associated with it. Here, just setting the properties of those objects, which are obviously different. Light is a color position. The geometric objects have an instance transformation associated with them. The camera has its own properties, and there's no reason here that these objects can't have subparts. So if this object was say the figure that we talked about in the last lecture, then down here at the bottom would be a whole tree, subtree, describing this would then point to the torso, and the torso would then have the head and the arms and the legs attached to it. So again, all I do is get a bigger tree, and I can traverse it just like we traversed the trees in the last lecture. And here again is where the property of where the traversal algorithm, if you're not careful, can matter. If I had multiple lights in here, suppose I had another little subtree with lights here, it might matter where how I actually traverse this tree. Although what a good scene graph will do is isolate things in a way that it will give you a consistent rendering, regardless of which order these things are done. Sometimes they're called, some of these nodes are called separator nodes, which the sort of a hidden node in here, which sort of says, okay, I'm going to start at the beginning, and this is the new beginning. This is a group, and over here would be another group. But we need not get into that here. Okay, so what does the traversal look like? Well, it looks something like this. You start with a scene, so you start with a new scene, and we'll see a real example of this. You put a light in, you specify the properties of the light, like its color, its position, its orientation. And now here's the important thing. It says, add that light into the scene. So you're defining an object here, and then you're placing it into the tree that describes the scene. Likewise, with an object here, what you're going to do is define all the properties of the object, and then add that object into the scene. And when you finally describe the entire scene, then you're going to apply the render method for the scene, which will wind up calling the render methods for each of the objects that are in the scene. So the light wouldn't have to be rendered, but on the other hand, the geometric object would have to be rendered. So that's the basic idea. In the next lecture, what we're going to do is look at some real scene graphs, and I'll show you one example from 3.js, which is the most popular one, scene graph for using with WebGL.